Good afternoon, everyone. We will resume the session. So, to summarize, category is a or consists of a collection of objects and a collection of morphisms or arrows, such that for every pair of objects, every ordered pair of objects x comma y, there is a particular collection of morphisms called the home set, or I won't call it set, called either C of x y, where C is a category. Categories. Collection of after the first. Identity with definition. So that that is not acts on the and don't any other group. That group that is what this is something. But again, that single category in which take a single partial order elements picked of category and that doesn't really have to be one morphism. Why does this flexibility an arrow arrow? Right? Arrows are actually arrows. So particular rotation. Arrow whenever add all of them. Actually, they're there in the pre-order. Suppose from I to X, A to D, there is arrow like that. Also there is, but there an arrow from already you, by definition the quantity to be this. But by definition, they're already equal. That's already equals. Identity property. Yeah. This is also X only. X to Z, the same arrow will be there. That composition. Because of this definition, not in category. There is at most one arrow in one order category. Ordered pair of objects, there is at most one. Their direction. The order category, if you take the order category, if you take third pair of objects, there is at most in one direction. I can add. Oh, not a problem. It's a order. So generally in a category, you start from group. And also another category that is not just because you have some homomorphism, that doesn't mean the order category, of course, we will see. Another nice again shows this need exactly. Here what you do is extra level arbitrary little real matrices says that real arbitrary R, it's still real matrices. R, okay. But the objects of the category are what? Are natural numbers. Object is a natural number. Collection of all morphism. I guess I am matrix. I matrix. Morphism from N to M. I N. The ring R. In this case, real ion matrix considered as a morphism. Considering you are not surprised. Several, several, in fact, R, if you take real matrices, so then axioms such as identity, of Correct order. 5 by 4 matrix by 4 by 2 matrix. After multiplication, identity by 2 matrix. Identity matrix. So that's a category. And when you come that's correct. So these should again point is there. Come back to that. Now, one of the definition of fact, like in this category, once you take an element, how do you prove 90? Normally, bijective function. How do you define things? Have this idea of that is that's that kind of thing. But actually take it. You have to do it. That property. I don't know this parallel paths. Directed path. on the diagram, this part of the diagram. That is, for example, it is triangle and commute. Commute. One. Later, this diagram comes. The I'll start dropping the local notation. Understand that is early. That is the meaning of circumference. Diagram is every such sub diagram comes wherever you can find. Maybe you have to look very carefully because triangle here. What does this diagram from where here? That should come here. That's not all. There is first composition. ADE and AC are already considered. Correct. You're correct. ADE and ABDE also have to consider. That's correct. That is another pair. Oh, all of them. Then that's it. Meaning will be implied by associativity. Specifically, AD, I don't have to come. Already, AD is equal to I will not going to. That's really this one. AC and A. That also I don't have to check. But Okay, now is it audible now? Clear enough? Okay, I'll continue. Just tell me if it's not. Okay, fine. Moving on. So, yeah, simple exercises for these. Here you have this. Can you see it as a tetrahedron or pyramid? You're able to see it in 3D, right? I mean, this broken arrow is, you have to think of it as behind the back face. Okay, so this triangle without directions I'm drawing, that is at the back, and this is the still not clear. Here, okay, now. So this is left, right. This is the back, okay, and this other triangle is the base. Okay, I hope you're able to see it. So anyway, the question is about this base or bottom. So left and right and bottom faces commute. Show that the back face also commutes. Left, right, bottom faces commute. Show back face also commutes. I can name the arrows if you want, so that you can speak. Say F, G, H, P, Q, R. Clear? The only things you can have are you can use are associativity, right? Because there's nothing, there's no identity or anything involved here. So just using associativity, how will you show? So first of all, what are you asked to prove? Back face commutes you have to prove. That means what? Back face is this one, F, H, G. Okay. So you're supposed to prove G composition F is equal to H. This is what you're required to prove. Okay. What is given? Left face commutes. That means left face commutes means PF is equal to R. Okay. Right face commutes. So QR is equal to H. Base commutes means bottom face commutes. So QP is equal to G. These three things are given to you. Okay. These are given. This is asked. Yes. PF is equal to R. Okay. PF is equal to R. Compose Q on both sides. So for now, I'll. Oh, all right. Sorry, I am actually not paying attention to the sides. So F is after P. Okay. Q after P makes sense. Correct. Yeah. Okay. So QR is actually equal to H because of this one. So far we have used this one once, this also once, and yeah, and then associativity tells you that this can be changed to QP F. So I'm explicitly showing associativity for the first example, but again, we take it for granted. So this is equal to G, GF. So GF is equal to H. So done. Okay. This is an example, but here actually we wrote everything in it. So the real idea of commutative or diagram chasing is you just look at the diagram and point and explain and then do it. Okay. For the online participants that will be difficult, but I'll try. So same proof, try to do it a little more visually. If you practice it, then later on you will be able to see it more quickly. Now first time if you're doing it for the first time, then of course you have to write it down and then train yourself with that. But if you have enough training, right, if you practice enough, then you'll be able to actually see it later on, okay, more easily. So here, for example, I know that I need to show H is equal to GF. So I start looking at that part, H. Okay. H is equal to GF is what I want to get. So I can see that in this triangle, GF is actually PQ. Okay. So if I want to go from here to, so I start with, okay, so H is actually just one object, right? I mean, one morphism, right? So I start with GF and then replace this single arrow using the commutativity of the base, the two arrows, P and Q. So again, this is how you should see it in your mind. Okay, you are seeing this part of the triangle in that direction, then that changes to this, that transforms to this. Okay, once you have this, observe that now you already changed this, so don't change it back to this. So the only other thing you can change is this part. Right, this part now becomes this single arrow by the commutativity of the left side. So therefore, you have this now, that is Q after R. Even without naming it, you can see it. And now also you know that right face commutes. So therefore, this is equal to the single arrow H. Okay, so it's like first you start with this, say the first step, then that becomes this as a second step, and yeah, that becomes this in the third step. Okay, so try to do it visually, but yeah, if you want to be careful, you have to write it down and check. Fine. But the thing is that sometimes you have very big diagrams, especially if you're doing homological algebra or something like that, or anyway, working with exact sequences and so you have, there are other properties there which you can use. So there also you may have big diagrams where it's tedious to write it down and check everything. Okay, but you observe that this part of the diagram commutes and so on. So now we'll derive some what you say, you will develop some basic tools which you can apply to larger commutative diagrams. So this is not the only thing you can do. You can make up laws for some of the things. So like here, for example, in these diagrams, check that if in each case, if both of the squares commute, then the outer rectangle also commutes. So actually that means you don't have to check so tediously with all the possible composition, you just have to check individually each square commutes. If that happens to be the case, then you're done. So again, what do you need to prove? That this, let me call this, okay, let me just call this F. Okay, G. So you need to check whether F is equal to G, given that each square commutes. That is given. So you have to start from one and get the other. It's LHS equal to RHS, but in diagrammatic form. can you get signature of the? No, that. Okay, done. This will become so one way. Okay, there are other ways also. You can start from the other side also. So if you've done it, then you can follow what I'm writing. It's actually somewhat trivial, right? Here I'm using the commutativity of the second square for the first question. I mean, first equation, using the fact that in the second square, those two are equal, right? So basically, if I start with f, and this comes this one because this square commutes. So now I have this, and then because this square commutes, that becomes, that's it. Okay. Again, you can write down the names and try. I mean, write it down carefully, but that's it basically. So here, f becomes this one, that becomes this because of first this square and this square. Okay. Second one, so firstly, what you have to verify for this to commute, these two need to be equal. Okay, the directions are different. Those two need to be equal. Okay. So even if you start from the smaller arrow, it still works because this one arrow can be replaced by this. One arrow can be replaced by that in the second square. If you're starting with the first smaller arrow, I mean, you can replace that single arrow by those three arrows. That path. Okay. Now once you have those, so this is first step. Second step is, so this to this is first step. Second step is this. Now you have this already there. This can be replaced with this one. Okay, that is the second step. Okay, so just write it here. Have the single arrow becomes these four arrows, and then this part. So that is here, and then this part becomes that. So again, just two steps. The third one, again, third one you have the outer rectangle is similar. Only the inner squares are different. Outer rectangle is similar to the first one, but inside it's different because this arrow is in the other direction. Okay. Again, what can you do? First one, right side. Okay, so you mean this one, right? On the right side. Okay, you want to start with the left side. Okay, start with this. Okay, then uh, this. Which arrow can you replace here? Yeah. Yeah. Okay. I'll. Yeah. A B C. Then you are starting with second box commutes. Yes. Yes. You can replace G by C E F. Yes. C E F. Right. C E F. G can be replaced by C E F. So then you have A B C E F. Right. Basically, that is this. So if I again without the names, if I want to, if I want to do it without names, then yeah, this first the one marked one, that becomes this. Okay, by replacing this part of that. Okay, and then of course you have this left square commutes, so that becomes yeah this. Okay, that this these three become that single arrow. Okay, so therefore I have this. Every case similar. That's just two. Wow. Okay. Similarly, if the inner triangle commutes and the three trapeziums, that is, these are what I mean by trapeziums, these commute, show that the outer triangle commutes. So what you're given is, this is given. This is given. Yeah. Those are all given. Okay, I think it's clearer without. I just wanted to show you what I mean by trapeziums and outer square and all. Okay, so those are all given. Yeah, I'll mark what you need to prove though. What you need to prove is this path equal to this path. Okay, I won't spend too much time on this because we have to go ahead to the bigger part. Okay. That's one way to do it. Okay. Yes. Okay. So let me move ahead. You can practice more of these. We'll actually do more interesting versions of these using some properties. So it's not just always associativity. There are other properties that you may be able to use. Again, especially as I mentioned, when you're doing dealing with exact sequences and such things, then you have to use some other properties like this. So as I asked earlier, how do you define isomorphism if you don't have access to elements of an object? You can't say bijective map. So just again, it'll seem trivial, but also it's very general. So a morphism F from A to B is an isomorphism in the category C if there exists a morphism G from B to A, but not just any morphism, such that G after F, when you apply G after F, that is equal to identity morphism of A. Okay. And F after G is the identity morphism of B. I can express this using a commutative diagram. This definition can be expressed using a commutative diagram. So I will say that. Okay, let me try to do it. I think yeah, we've already seen this because in groups and yeah, in groups or maybe no. This is F. Sorry. Yeah. So F is an isomorphism if there exists. So when you want to say there exists, usually you use it. Usually you show it using a dashed arrow. It's not mandatory, but usually you show that using mandatory. So if there exists a morphism G from B to A such that this diagram commutes, then F is an isomorphism. Is that the same as the definition written here? So I'm using 1x instead of IDX or 1A instead of IDA. Okay, but it's just alternative notation. You can use either notation. Sometimes you use ID to be clear because the object you're talking about may be something like a group which contains an element named 1. So otherwise I'll just use 1 for the morphism itself. Okay, so is this the same as what is written there? If this diagram commutes, what does it mean? Means all the sub diagrams also should commute. That's me. So here, what are parallel paths that you can find? For example, here is one. This is one path. This is another path from A to A. So there are two paths from A to A. One is G after F. Another is just 1A. So to say that this commutes, you're saying GF is equal to 1A. Okay. So, oh, this is written wrongly. Sorry. This should be FG. Yeah. GF is equal to 1A. Sorry, please correct that. Okay. It's FG. Similarly, the other triangle, this also should commute. That means here there are two paths from B to itself. Okay, there are two paths from. I think I put the wrong direction there. Oh wait, I think this is the wrong direction. This should be. Sorry, the other one doesn't make sense at all. You can't have a directed cycle like that. So this is the correct one. Okay. So here there are two paths from B itself. Maybe these two parallel paths. Okay. So one is this F after G. The other is 1B. So these should be equal. So that gives you the other. Okay. So the diagram expresses the definition. So if there is an isomorphism, usual things, if there is an isomorphism, then you say that the object is isomorphic. And of course, if F is an isomorphism, then that corresponding morphism G is also an isomorphism. Then you can show that G is the unique one satisfying this. We don't insist on uniqueness in the definition. It follows. There are some definitions where we insist on uniqueness in the definition. Here it follows. Because again, usual thing, you can compose it in two different ways and then associativity, and then that will give you that. That also can be proved using commutative diagram itself, the uniqueness of G. Anyway, you can prove that G is unique corresponding to F. So every F, if it is an isomorphism, it has a unique inverse F inverse such that F inverse is F. So all the usual things follow. This is just terminology. Endomorphism is a morphism from X to itself. Automorphism is an isomorphism from X to itself. So these all the usual terminology applies in general in a category. Okay. These are two other things which we may not be completely familiar with, or we may have special cases, but the general definition is a bit different from the special cases. So usually you may call something monomorphism if it is an injective homomorphism. But yes. Okay. Okay, I'll discuss that. So you are in the category of groups. If you treat groups as sets or something else, then it makes no sense. You have to treat them as groups, which means as objects of the category of groups. In the category of groups, what are the morphisms? Group homomorphisms. So there, if you have G and H, if you have a morphism from G to H, that means it's a group homomorphism. Then if you have another morphism from H to G, that means there's a homomorphism from H to G. And these compositions should be identity, which implies that as functions they are bijective. So they become bijective homomorphisms, and therefore. But here's the thing. If I use this definition, that being careful about the monotone map or homeomorphism, I don't have to be so careful because it will automatically follow. What I mean is this. Suppose now, instead of group, you take the category of posets, okay? Not single poset as category of all posets. In this category, the morphisms are monotone maps. Now, what does it mean for a morphism to be an isomorphism? So there is a monotone map F from P to Q. What does it mean for it to be isomorphism? That there is a morphism G from Q to P such that the compositions on the two sides are identities. But if I say there's a morphism G from Q to P in this category, what is that morphism G? It is a monotone map. So automatically it becomes a monotone map. Whereas if I say F is a bijective monotone map, that is not enough. Bijective monotone map implies that there is a bijection from Q to P which is inverse of F as a function, but not necessarily as a morphism of this category. So automatically, so whatever new algebraic structure you define, or not algebraic, any other structure you define also, right? The definition will apply to that also. But you have to, whatever morphism you define, that is what defines the structure of your category, of the objects in your category. So there automatically you will have to say that this is a morphism of the correct kind according to your definition, specific definition. But this is enough. This satisfies, this ensures that whatever notion of objects and morphisms you have, this will be an isomorphism that preserves that structure which you are studying. If it doesn't, then that means your morphism is not defined correctly. Okay, for example, in topological space like this, if you don't take continuous maps between topological space, then the actual thing that you're studying won't be preserved. The actual properties of topology that you want to study won't be preserved if you take any maps instead of continuous maps. That is the thing. Okay. Yeah, so again, topology, if you take F as a continuous map, G has to be a continuous map in order for it to be a member of this category. Otherwise, it will be merely a function. Yeah, that's what. Okay. Yeah, now what is a monomorphism in a general category? Because again, you cannot say injective homomorphism or surjective homomorphism. So it is defined in this way. MF. So what is that? XY, right? Okay. So a morphism F from X to Y is said to be a monomorphism, or as an adjective, you can say it is monic. Or sometimes shorten monomorphism to say it's a mono. Okay. So that means suppose you have two maps, two morphisms from one object Z to an object Z X such that Fg is equal to Fh. Suppose then you can cancel F and say G is equal to H. That means, in other words, a monomorphism is a left cancelable morphism. That's it. Algebraically, you can just say it is cancelable on the left. We are not saying it has a left inverse. That's different. If it has a left inverse, then it's left cancelable. But the converse is not true. It is simply a left cancelable morphism. Okay. So simply means cancelable on the left side. So similarly, epimorphism is cancelable on the right side. So for that, what will it look like? You have X to Y, and then Y to Z. You have, suppose, two maps such that, okay, this is only if it is given. If this is given, then you should have G equal to X. So here, I changed the notation from what I had written. Sorry, I'll make it consistent with what I already. What I wrote is not incorrect, but if you read this and look at the diagram, it will look different. Okay, so here I used F and G again. Okay. Yeah, so here you have if F is equal to G. I'm not saying that they should be equal. Suppose they are equal, then the only way is F is equal to G. That means if F and G are not the same morphism, then Fe cannot be equal to G. Okay, again, cancelability, that's it, right? Cancelability. But do not consider cancelability as invertibility. If you can cancel two elements, does it mean they have, if you can cancel one element, does it mean it has an inverse? For example, in Z, or not Z, let's say natural numbers, strictly positive numbers. Multiplication, you can cancel anything. If Ax equal to Bx, A equal to B. But does it mean every element has an inverse in the set? No. So cancelability is not the same as invertibility. Invertibility implies cancelability, not vice versa. Okay. Just keep that in mind. Okay. So if you define left invertible, that's a stronger thing. That will be a section. And the other one, right invertible will be retraction. Again, you don't need to remember these names, so leave it. Unless you come across them in a particular thing, don't try to remember. Okay. Monomorphism and epimorphism are more important. So what does this generalize actually from our familiar things? Monomorphism is a generalization of what idea? What kind of functions? Injective functions, injections. Okay, so these generalize injections, one functions, right? One. And epimorphisms generalize, obviously, the other one, surjections. But here you have to be careful. When you say they generalize, obviously, not just functions, but morphisms. However, it is not always true that in any category, a monomorphism is necessarily an injective homomorphism. That is not true. It's not true in general that a monomorphism in an arbitrary category, in which objects are sets and morphisms are some kind of functions, some structure preserving functions. It is not always true that monomorphism is a injective homomorphism or epimorphism is a surjective homomorphism. Other way is true though. If you happen to have a surjective homomorphism, it will be an epimorphism. If you happen to have an injective homomorphism, it will be a monomorphism in that category. Okay, if your category consists of objects and sets and functions, like here, there is our I think here goes. In this category again, the morphisms are not functions, objects are not sets. So what does it mean for some morphism to be monic? We have some morphism from, okay, let's take a specific case, the 3 to 5, let's say. You don't have to go to 4. 3 to 5 also there are morphisms, right? So 3 to 5, suppose I say, I'll use capital M because they are matrices. What does it mean for this to be monic? Yes. So we have some arbitrary n, let's say. Yes. So you should have a matrix, a 5 by 3 matrix, which can be cancelled on the left. It is not guaranteed that this exists. These are monomorphism and epimorphism, just definitions. There is no guarantee of the existence. If they exist, they are called so. Okay. So is it possible in this case? Can you have a 5 by 3 matrix, which is left, no matter what n you take, right? This can be any 3 by n matrix, and whatever whatever A and B matrices you take. So is it true? Is it possible? 5 by 3. 5 by 3, what rank can it have? 3, maximum 3. If it has rank 3, that means it is full column rank. Full column rank means, obviously, actually, in the case of matrices, cancellability is equivalent to invertibility, but left or right. Okay, not full invertibility, left or right. So if you want left inverse, yeah, it is possible. You can definitely have. So given a full rank matrix, okay, suppose there are 3 linearly independent columns, then you can have a 3 by 5 matrix such that this product is identity matrix of order 3. So if left in was, this is definitely true for, okay, not for arbitrary R, but at least for real R. Okay, or at least over a field, whatever field you take, it works. So if you take any field, not arbitrary unital ring, any field, this is definitely true. Such a matrix, if it happens to have full column rank, means rank 3, then it has a left inverse, and then it will be left cancelable, and it's also if and only if. In this particular case, it is left cancelability and left invertibility are the same. In the category of sets, left cancelability and left invertibility are the same. That's why injective functions are exactly the left cancelable functions, which are also the left invertible functions. These 3 different things, one of them you can only define in sets, injectivity. You can't define in arbitrary category. Left cancelability and left invertibility you can define in any category. They don't always agree. One does not always, invertibility implies cancelability, not the other. In the category of sets, these 3 are equivalent. Right cancelability, right invertibility, right surjectivity. These are all equivalent. Even in the category of vector space and linear transformations, these are equivalent. Okay, vector space, not modules, vector space. So you have fields. Right? So these are equivalent. Okay, just to now using this, you can have more interesting problems on commutative diagrams. So now in this diagram, which is one of the diagrams we saw before, it is given that outer rectangle commutes, not that the 2 inner squares commute. It is given that the outer rectangle commutes. Then, yeah, you have to show that the diagram commutes either if A is epimorphism or M is monomorphism. So each case separately. Suppose it is given that M is a monomorphism. M is a monomorphism means you have this is Q in the first case. Using this, you have to prove that outer triangle commutes is given. Using these two things, so this is given. Oh, right. I think so. Let me think about this. One more square. Oh, yeah. Outer square is not enough. That's correct. I'm sorry. I should add that. Yeah, I'll add that here. M is monic. And the first one, does it? See, you cannot get that MF equal to MG. If it is given that MF equal to MG, you can say F equal to. But okay, is there any way? Because did I misread the question? Actually, I'll check. Okay. Wait, hold on. I'll label him. Okay, fine. But see, in order to use this, you have to have something with M composed with two different things. So somewhere you must have M after something, and on the other side M after something else. Only then you can conclude anything from this property. So if that is not already there, yeah, that's what you cannot cancel, or you cannot invert. You can cancel but not invert. That is a problem. Invertibility is not there. So you have this, but that does not allow you to do anything because you cannot use inverses. Okay, so yeah, I definitely missed something when. Oh, right. Yeah, I did miss that. Yeah. So M is monic and left square commutes. Yes. Yeah, please add this to question. Yeah, so that's a question. In the first case, left square commutes is given. So FE is equal to BE. So you need to show MBA is equal to DCE. No, sorry, that is also given. You need to show right square commutes, right? You need to show that MF is equal to DC. Okay, MF is equal to DC. Since is it MF is okay? Let me write it down and check. You know that MBA, yeah, that's correct. MBA is equal to DCE because left square commutes. I think again I need to interchange this. Probably that's probably correct. Yes. Yes. Okay. So MBA is equal to DCE. That can be changed to MFE is equal to DCE only. This side doesn't change. Um, yeah, it is given that right square commutes. Wait. Yeah, left square commutes. I didn't. This side I need to change. What? MBA remains as it is. This side changes to MFE. Yeah, correct. Huh? Sorry. This is correct. See, if monic is given, then I need to get M on both sides on the left side. LHS and RHS left side. So if I start with MBA equal to DCE, DCE can be changed. Okay, DCE can be changed because it is given the right square commutes, this one. So DCE can be changed to MFE. Then M can be cancelled. Okay. So then by cancellation, BA is equal to FE. Does that follow? You follow? Once again, I'll do it once again. Sorry about the confusion. So I'll start over here. If you want to listen here, it is given that the outer square commutes. Okay. So this outer rectangle commutes. That is, these are equal. That is given to me. That means ECD is equal to MBA. Okay, I mean actually DCE composition is equal to MBA composition. That is given. Also, it is given that M is monic and right square commutes. Right square commutes means whenever I get this particular square, I can change any path to the other path. So DC and MF can be interchanged whenever I want. If I have DC or MF, I can change for the other. So I want to prove that. So already the one rectangle and the square commute, right? So I just no order no. Yeah, I just need to show that FE is equal to BA. Okay. So the question is FE is equal to BA. Start with MFE. Okay. Why? Because I have to somewhere use the fact that M is monic. The only way I can use M is monic is to cancel it on the left. So I have to start with something where M is on the left. Or that's a good way to start. So I'd start with MFE, and then that is actually or MBA rather, because what I have is this rectangle. So I'll start with MBA, and that is equal to DCE because of the commutativity of the rectangle. So MBA is equal to DCE. Now I can use this smaller square. So in that I said that I can freely interchange DC with MF. So now changing that, I get MFE. But now M is on the left side of both sides of the equation. Okay, so therefore I can cancel it. Now that I have this, I can cancel it and say BA is equal to FE because it is left cancelable. That's the meaning of monicity or monomorphism, right? Okay. Similarly, the other one, let me move on because it's already 3:30. Similar question. You can just note it down and try later. 30. Okay, try later. I'll go on to. Now, if you already have one category, you can construct other categories from this. Again, this will give you examples. Even if you start from a concrete category, concrete meaning its objects are sets and morphisms are some kinds of functions. Okay, some structured sets and structure preserving functions. So even if you start with the concrete category, these constructions will give you categories where objects are not just sets and morphisms are not just functions. They may be something like some particular special collections of sets and collections of functions or something of that sort. Okay. So one example is this, the slice category. So if you have a category C and A is an object of C, so you can think of set as a particular example, the category of sets, and A is a set, is a particular set. Then the objects of this new category C over A, it's a slice category. It's not quotient at all. You don't think of it as quotient. The category C over A, you can also denote it like this if you want. Okay. The C stands for the category's name. So in this case, it would be set over A. Okay. A is a particular set. Is all the basically they're all morphisms. Okay, from arbitrary objects to A. We denote it as a pair consisting of an object and a morphism. You can just think of it as a morphism because a morphism contains the data of what its codomain and domain are. But for simplicity, we denote it, or for clarity, we denote the domain explicitly. Okay, but they are basically you take any A, like shown here. This is one object. Okay, this is another object. Okay. So now, if these two are objects of your category, new category, okay, the objects themselves are morphisms of some other category, but here they become objects. Then you have to define composition. I mean, you have to define morphisms first of all between these objects. So you define a morphism using again morphisms from the original category, but not all of them, only one satisfying some condition. What condition should they satisfy? That you say that M is a morphism from XF to YG if in the original, so in C over A, M is a morphism from this to this. If in C, M is, so C is already fixed. You are not deciding what the objects and morphisms are there. C is already given to you. So if in C, M is a morphism from X to Y such that this diagram commutes. That is such that G after M is equal to F. Okay. Why do you have this condition rather than taking arbitrary morphisms? Because here you went to the trouble of taking morphisms as objects. So this morphism you want it to be in some sense structure preserving. So structure preserving means here the only thing you can do is, because again you don't have internal structure, the only thing you can do is this commutativity. Okay. So again, you need to work on why that intuition is correct one. Yeah, of course you can change the definition, get some other category, but this definition intuitively it makes some sense. Okay, so it's defined in this particular, and it can actually have some uses when you think about it in light of other definitions. Okay, so this is a new category called slice category. The thing is, again, you have to check whether the axes work. So suppose you have like F, G, H, or no, or rather XF, YG, ZH. These are three objects in this category. And suppose there are morphisms like M from here, N from here to here. Can you define their composition? That is the question. So what will it look like here? You have X to A, that is XF. Okay. Now YG means, again, every morphism, every object here is a morphism into A. So YG means Y to A, G is there. And should have drawn that in the middle. So YG means Y to A, there is G morphism, and Z to A, there is H morphism. In the original, these are morphisms in the original category. Now they are objects. Yes. Yes. In C. Yes. No, because they are things of objects of different category. It is like saying the set of integers. It is a group under addition. It is a ring under addition and multiplication, or it's a semi-group under multiplication. It's totally different, right? We are using the same name repeatedly, but they are all considered as different things. You can't equate them at all. You can't say whether the group of integers and the semi-group of integers, is there any relation between them? Not really. They share the same set, but as mathematical structures, there is no comparison possible between them. Similarly, here, you are just reusing that name. The original or the origin of M is as a morphism of the original category C. But now you upgraded it to a morphism in this. You are reusing the same name, but it's no longer considered as the same thing. So you can't ask whether they're equal. Yes. Hmm. Hmm. Any such morphism that makes this triangle commute. So many. Yeah. It's not a single one. Any morphism of C such that this diagram commutes is considered to be a morphism from this particular object to this particular. For example, another example, like from X itself in C, there might be some other morphism to A. So in fact, these are now two different morphisms. Two different objects in C over A. One morphism from X to A, another morphism from X to A. These are two different objects. Okay, although you draw them like this, but they're really two different objects of this slice category. And so it is even possible to have a morphism from this object to this object. But what will it be? In the original category, it has to be a morphism from X to X, such that this commutes. Now, if you take F again, if you take F prime is equal to F, then identity morphism is one such. There may be more. Okay, there may be more, but identity morphism is one such. Okay. Okay, so composition. So if you have a morphism from X to Y, from XF to YG, that would mean that in the original category C, you have a morphism from X to Y, but such that this triangle commutes. So this M is originally a morphism in C. This is in C. Okay. But such that this triangle commutes. Similarly, you may have one morphism N from YG to ZH. That means again that in the original category, there is some morphism from Y to Z, but it happens that when you put it here, this commutes. Like Hn is equal to G. Now, can you define composition of Nm? So suppose you simply define the original composition of Nm. You try to define it as N composed with N as in the original category. But in order for it to be a morphism of this category, this diagram should commute. Will it commute? Yeah, because these two triangles commute. This outer one will commute. So composition is well defined. Associativity follows immediately because composition is not really a new composition, it's same. Identity element will always be there. Again, identity morphism will be there. So, okay, not much time. I want to finish by 4:15 at least. So, I'll go ahead. But this I will do because it leads to something else. This is just the previous one was done because this is an upgraded version, but this is more important than the other. Okay. Here now, so you can do this with any number of objects and any number of morphisms. So here, So we're defining, this can also be denoted by C over AB if you want. Okay, but I'm using this notation. Actually, to be consistent, I should use same kind of notation. Right? So you have some category C with objects A, B, X, Y, Z, and so on. And so many morphisms between them. Okay, whatever. But now I'm taking this particular A and B, which are of interest to me, and defining a new category in which the objects are pairs of morphisms, or really I can fix a domain and then pair of morphisms. So take X and then a pair of morphisms from A to B. Call them F A and FB. Okay. Yeah, that's it. No other condition, just this. But this is one object. Maybe I'll make space to. Oh yeah, actually fine, because I'll draw Y after X, so it's fine. Yeah, this is fine. So now another possible object. So this is, remember that this happens to be a single object in the new category. Okay, for the same X, if I use a different function, either FA or FB or both, I will get different object for the same X. So it is not, objects in this are not indexed by X. It is this triple. So any one of them, if I change, okay, if I change, I have to change these also. But even if I change one of these, I get a new object. Anyway, that don't need to worry. Another possible object is some Y possibly equal to X, and a pair of functions, I mean morphisms, not functions, morphisms from Y to A. Again, I need to define a morphism in this category. So now this is again a single object in this new category. In order to define a morphism in this new category, I will say a morphism from this triple X, FA, so X, FA, FB to Y, GA, GP is, again I have to use something, right, which is defined in an arbitrary category. So only thing I can use is morphisms of the original category. So I will say it is the same as, let me say this is an upgraded version. So if you want, I can use a different notation, but it's really the same thing. So it's a morphism from X to Y in C. Okay. But with what condition? The resulting diagram, those two triangles should commute. So this should commute and this should commute. Only then I will call it a morphism. Only then I will consider it a morphism. To take an arbitrary morphism from X to Y, it is not a morphism from this triple to that triple. Because then I'm not using the, if I allow any arbitrary morphism from X to Y to be a morphism here, then I don't use this information at all. I'm just taking it without any use, right? So the point is somehow you involve them. Okay. So these are comma categories, a more general name. These are two particular comma categories. Even the previous one, co-slice, slice, co-slice, they are also comma categories. Okay, we'll come back. This will appear later. Okay, this is a very broad question. So it is asking you to define something. Obviously, you can define anything you want, but what should be the sensible definition is a question. So to check whether your intuition is correct, I want to now define. So C is some category. There are so many morphisms. C. I want to define a new category in which the objects are morphisms of C without any condition. Any morphism you take, that becomes an object here. So this particular morphism is an object. If I take, say, this particular morphism, that is also an object. Now I want to define a morphism from this object to this object. What should I do? How can I connect them? You need what? You have to use two morphisms from the original category. Because you need to connect X to A, Y to B. So now your morphism from F to G. Okay. Is really a pair of morphisms, one from X to Y, the other, sorry, not X to Y, X to A, and another from A to B, where actually this, like I should really say, domain of F to domain of G, codomain of F to codomain of G. That's a general way of writing. Here I've denoted it, such that the square commutes. Such that the square commutes. Okay, those will be morphisms. Again, composition will work if you like just compose both of them. So if you have another one like n1, n2 to some other CD, now this square should commute for n1 and n2 to be morphisms. But for the composition to work, this outer rectangle should commute. You already proved that earlier. These two squares commute, the outer rectangle will commute. So that will work. Composition will work. Okay. So we saw opposite of the order. In the same way, you have duality in categories, where you define the opposite of a category to be another category with nominally the same objects. You don't change the names of the objects, but you every morphism in the original category, now you consider it as a morphism in the reverse direction. So in C, if you have morphism from X to Y, C, you will consider this. So this is M. You can call it M op if you want, or just M itself. M op is better. You consider it as a morphism from Y to X. So again, there's no question asking how this can be done. We are just calling it so. We are just considering it as a morphism in the opposite direction. But it's not very strange. Suppose you have a function from A to B in the category of sets. I want to say that this is a morphism from B to A. It is not that I'm taking F inverse. This itself, I'm considering it as a morphism from B to A. Can it be done? I mean, it's just a matter of naming it so. But can you give any meaning to this? What is really a function? Ordered pairs. Function is just a set of ordered pairs satisfying a particular condition. I can consider the ordered pairs in the opposite direction, right, in the reverse direction. So it is a relation. So this will be a relation satisfying the other property. Like function means left total, right unique. Left total, right unique relation. So if I go to the opposite category of sets, they will consist of the opposite category of sets consists of sets together with relations that are right total, left unique. Okay, that's it. So it's always possible to do that. Yeah. So okay. What did you order finally? Cutlet. But only tea coffee. What? What did you order finally? Huh? ठीक है okay okay so we have Cartesian product of sets, direct products of groups, direct products of rings, and so on. In some cases, you don't have direct products of fields is not there. Correct. So, how can we generalize this to a category? If you want to try to generalize this construction, starting with Cartesian product of two sets only, if you want to import this into a category setting, you have to free it of elements. So, how do you normally define Cartesian product of A and B? Set of all ordered pairs. First element from A, second element from B. What property does it have that characterizes this set? So I need to now say that given two sets A and B, is A cross B. In fact, I'll call it P instead of, because the notation should not suggest that we are using this. So I want to say P is the product of A and B if it satisfies some property, but without using elements. I can use functions. I can use any number of sets I want, but I cannot use elements. How to characterize this? Firstly, from the product, you know actually by looking at the definition, there are two projection maps. Say pi 1 and pi 2 or pi A and pi B project onto the first and second component respectively. That means it sends an ordered pair AB to A for pi A and B for pi B. Okay, so these are just functions. So I can just say there should exist functions pi A and pi B from P to A and B. But not just any functions, because so many sets will have functions into them, right? So what other property can I use for characterize? Suppose, for example, I have some set X. I have two functions, say FA and FB. I give you functions from X to A and B. Can I somehow write FA and FB in terms of pi A and pi B? So FA maps elements, so X maps to FA of X and X maps to FA of X, means this is in A, this is in B under the two mappings. Okay. Can I somehow use these projections to define some other map so that this, yes, X to P. So X to P I can define some function. What function? I'll call it FA cross. No, I'll call it FA comma FB. Okay, I'll call it FA comma FB. But what should it do? It should send X to. But how? I mean, with the actual definition, in the final definition, I won't say what it does. I'll just say there exists. But here, you know what it should do. Yeah, it should send it to, because this is P, no? A cross B is actually P. So basically, this says that I can send X to F of FA of X, comma, FB of X, which will be an element of the Cartesian product. Again, this is only in sets. When I generalize, that won't be there. I won't say that. But the idea is for any such, so for all such triples, for all such triples, mean, for each one, there exists, in fact, a unique mapping from X to P such that this commutes. Because now this will commute. Pi A applied after this function, what will it give me? If I take this and then project to the first component, I will just get Fa of X. That means that composition is equal to Fa. Pi B after this Fa comma Fb is just Fb. So this, and this is a unique function satisfying this. Okay. So this is a characterization of the Cartesian product in the category of sets. There is a unique one. But then suppose you take B cross A and then take pi B comma pi A as solutions. So then this will also satisfy the same. Like if I change the order in the name, okay, just B cross A. This will also satisfy the same property. So does it mean there are two Cartesian products for A? I mean for AB? Actually, I don't even have to use A cross B. I can use some other set with the same number of elements and then define pi A and pi B appropriately. So even that will satisfy the property. But that's okay because they will all be isomorphic to each other. As sets, that means there will be bijections between them, natural bijections between them. So that really, only these functions matter. The actual elements of the set, the names of the elements don't matter. It is only these functions that matter. So this definition now can be generalized to a category setting where, I'll say it here itself. So I just erase these things. These particular definitions and define it as a property I'll just say, okay, without giving it more structure. For every triple, so first of all, a product of A and B okay. Yeah. So product of A and B, two objects A and B in a category C, is an object P of the category C together with two morphisms pi A from P to A, pi B from P to B. So this also a triple. This triple is the product, not just the object. This is the product if it satisfies the property that for all X comma Fa comma Fb with this signature, there exists a unique morphism M from X to P such that this commutes. Is this similar to some definition you saw before? Any definition that you've seen before? In a pre-order or partial order? What is the meet of A and B? It is an element which is less than or equal to both A and B. So it's a lower bound of A and B, but additionally satisfying what property? If you have any other element, any other lower bound, then that is also less than or equal to A and B. Compare. So this is lower bound kind of, but more general because it's just not just that there is some morphism, but there are morphisms, particular morphisms. Here there are anyway at most one morphism from one object to another, right? So here there is a morphism from P to A and P to B such that whenever you have two morphisms from some X to A and B, that will factor through this uniquely, through a unique morphism. Okay. So this is the characterization of products in category. You can check that if you replace these by groups and group homomorphisms, you will get the direct products of groups. Similarly, rings. Okay. And if you try to do it for and vector spaces also, if you try to do it for a field, it will fail. You will not get, the existence won't be there for fields. Groups and sets and all, you can prove by construction that it exists. But for fields, it won't be there. You can get the product as a ring. Direct product of two fields is a ring. Z2 cross Z2 is not a field. It's a ring. It exists, but not in the category of fields. So like that. Okay. So again, when you define some new mathematical structure, this is how you should define the product. You have defined some new mathematical structure of your own. This is the first product you should define. There are other kinds of products, but this is the basic categorical product. Okay. Similarly, by duality, what can you do? Just reverse all the arrows. You will get something else called the coproduct. Okay, so this definition immediately leads to another definition called the coproduct. So in the category of sets, the coproduct of two sets is disjoint union. Coproduct of two vector spaces is the direct sum of the vector spaces. Because vector spaces form what is called an abelian category, coproduct and product turn out to be, as objects, they are the same. The morphisms will be different because in coproduct you will have the injections from the objects into the coproduct. Okay, but other than that, the objects will be same in vector spaces. If you take the category of abelian groups, then the coproduct will again turn out to be direct product, which is direct sum. But in the category of groups, if you have non-commutative groups, also category of groups, the coproduct of two groups is something called a free product, which you need to really see what it is. Okay, it's little, not too difficult, but slightly complicated definition. It's not a familiar construction because it will always turn out to be an infinite group. Even if you take finite groups, you will get an infinite group. So if you're familiar with tensor products, again, tensor product, yeah, in the category of rings, unital rings and ring homomorphisms, the coproduct of two rings is not the direct sum, but the tensor product. We call it direct sum because it's similar to vector space and all that, but that is just the direct product for a finite case. Okay, but the real coproduct in the category of unital rings and ring homomorphisms is tensor product, R and S, which you can define in modules also. Okay. Again, the direct sum there is tensor product. Okay, fine. We'll then stop. I can't do unit element junctions in general. I can't do, so we'll stop. Thank you. So for the online participants, we have finished, we have concluded the workshop. Thank you for joining, everyone. Oh. Yes, do you have a question? You can unmute and ask. I have allowed to unmute. Yes, you can. I have allowed you to unmute. Please ask your question if you have any. Oh, I'm sorry. Are you asking? No, anyway, you're not asking. by mistake, I guess. For information, these are duplicates. I told you, these are duplicates. No budget for duplicates. So they have paid their own money and travel and come and even accommodation also they are only paid. That is much. Come from investors. You really want that gift?